Okay, so am I audible? So good evening, everyone.
Good evening, sir.
Yeah, good evening. So, so on previous class we were discussing induction and well ordering principle, and we also talked about Euclid's algorithm, which uh, which we can uh, which we can utilize to generate the coefficients for Wijau's theorem, and and I gave you a few exercises too, as far as I remember. Yeah, so these were the three exercises. I hope no one had difficulty solving them, right? Like the second one was exactly same as the first one, and the first one is exactly same as the squared example that we did in class. 1 squared plus 2 squared. And the last one was also obvious from the fact that since if in the inductive step we have n 2 power n less than n factorial as our assumption, and then we multiply 2 on both sides. So we get twice n factorial on RHS, and LHS is 2 power n plus 1. Now, since this is not the base case, or we can anyways take n equals to 2 as the base case. So here we have n is strictly greater than 2 in the inductive step. So that means multiply this by, or n plus 1 is strictly greater than 2. So multiply that by n factorial on both sides, we get n factorial plus, I mean, n plus 1 factorial is greater than twice n factorial. So this thing is smaller than n plus 1 factorial. So that shows the inductive steps. Okay, so yeah, so let's continue with a few more examples and exercises before we move on to the next things. So we have been introduced to congruences. So can you solve this question? Suppose 13 power 17 plus 14 power 3 is divided by 11. Then what's the remainder? So these are pretty common question. So without the help of congruence, it's probably almost impossible to solve such questions. Yes, some binomial tricks do apply, but they're pretty rare. So the idea is to use the fact that a power x is congruent to r power x mod n if a is congruent to r mod n. The exponential property of congruence. Right? These hold for all a n in integers, naturals. So here we have 13 congruent to 2 mod 11 and 14 congruent to 3 modulo 11. So taking powers 73 and 3 respectively, we have 3 power 73. Yeah, so you see, we still can't compute 2 power 73 that easily. So you have to keep on continuing this process of taking remainders and taking small powers till we reach 73. So let's see what's what's 2 power 4 is. So 2 power 4 is 16. So 2 power 4 is 3 power 4. Yeah, that's the same thing. So it's 16. So these are all under congruence. So that's 4 mod 11. Then we can let's write down powers of 2. Yeah, 2, 4, 8, 16. Yeah, 32. So 32 is a nice spot since it's just one less than the next number, 33, which is a multiple of 11. So 11's multiple. So that's 2 power 5, I suppose. So 13 power 5 is congruent to 2 power 5 is congruent to 33 is congruent to minus 1 mod 11. Right. So we get a remainder of 10 when we divide 13 power 5 by 11. That's what this line says. So now we know we can write 13 power 73 as 13 power 5 whole power up till 70 we can do so. That's 15 times 13 cube. So that's congruent to minus 1 power 15 times 13 cube. Minus 1 power 15 is minus 1, so minus 13 cube. And we know 13 is like 2, so it's minus 2 cube. So that's minus 8. If we add 11 both sides, we get 3. So the first term gives a remainder of 3 when divided by 11. So 13 power 73 gives a remainder of 3. Right, so anyone has any doubt why this works? So this is all due to the properties of congruence. Next with 14. Okay, so 14 is just 3, right? So 14 cube is 3 cube, that's 27, that's 5. Did I made any errors? I mean calculating errors or something? So 2 power 5 is minus 1 modulo 11. So 73, so we have 5 times 15, that's 70. Oh yeah, sorry, that's 7. It's not 5 times 15, it's 5 times 40. So we have minus 1 power 14 times 13 power 3, that's plus 13 cube. So that's plus 2 cube. 2 cube is 8. It's nothing negative, it's plus 8. Sorry for that. So 8 and 5. So we get a remainder of 3. Okay. So 13 power 73 plus 14 cube is congruent to 8 plus 3. Sorry, 8 plus 5. That's so 2 is the answer. Okay, so now try solving the next one yourself. So find the remainder when 2 power 70 plus 3 power 70 is divided by 13. I'll just wait for 5 minutes. Everyone please try the problem. So. Yeah, so what's the remainder? Anyone? Let me ask someone. Shagnik Bhattacharya, can you reply? So please unmute yourself.
Sir, I was trying this song, but I was actually unable to do it.
Sorry, can you
Sir, I
repeat?
was trying to do this song, but I was actually unable to do this.
Okay, so you started. So how did you start to solve the problem? Like as you just saw in the previous one, we tried to find the suitable power of the bases or the remainder of the bases, so that it's just plus or minus one of that device, right? Which is 13 in this case. So can you guess an exponent of 2 which is plus or minus 1 of 13? So we have to guess the power. So let's write down the powers of 2. So we have 2, then 4, then 8, then 16, then 32, then 64. Yeah, and so we know 13 times 5 is 65, right? So 64 is just minus 1 of that. So we have 2 power 6 is congruent to minus 1 mod 13, since like 2 power 6 can be written as 13 times 6 plus 12, or 13 times, sorry, 13 times 6 minus 1, or 13 times 5 plus 12. Is that so? No, no, sorry, sorry. This one is 5. This one is 5. This one is 4. Right, so the remainder is either minus 1 or 12, whichever you prefer to write it as. In our case, we are trying to reduce the like simplify the expression, so we will use the minus 1. So 2 power 6. Now let's divide 70 by 6. So we get 6 ones, so 6 and 10, so 6 twos are 70. Sorry, 6 elevens are 66. We get a remainder of 4. So it's 2 power 6 whole power 11 times 2 power 4. 2 power 70 can be presented as minus 1 power 11 times 2 power 4 is 16. So it's minus 16, which is in turn congruent to minus 3 mod 13. Similarly, for the second term, 3 power 70, we again write down the powers of 3. So 3, 9, 27, 81. And okay, so for 13, we have 13 ones are 13, 13 twos are 26, and this is 27. So we know that 3 cube is equal to 27, which is congruent to 1 mod 13. So 3 power 70 is equal to 3 power 3 whole power 69. So that's 23 times 3. This is congruent to 1 power 23, congruent to 3 mod. 13. So 2 power 70 plus 3 power 70 is congruent to minus 3 plus 3, which is 0. Right, so 13 divides the expression. So the remainder is 0 and 13 divides 2 power 70 plus 3 power 70. It was the proof, we just needed to solve this. So the answer is 0. Okay. So let's move on to a new topic now, quadratic residue. So what are quadratic residues? Well, it's nothing. It's just what the name signifies. These are the remainders when perfect squares are divided by something. This something can be any number, like mostly it's a prime number. So if we have a prime p, and the natural number a, then a square is congruent to x mod p. So if like a square is congruent to x mod p, we say x is a quadratic residue modulo p. For an example, let's take the number 5 as p. So let's find the first few perfect squares. Let's find the remainders given by the first few perfect squares. So we have 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, 7 squared. That's enough, I guess. So 1 squared is 1. When divided by 5, it gives 1. 2 squared is 4. When divided by 5, it gives 4. It is also equal to minus 1 mod 5. 3 squared is 9, which is also 4. Also minus 1, you can see. Then 4 squared is 16, which is 1. 5 squared is 0, of course. 6 squared is 36, which is again 1. And 7 squared is 49, which is again 4 or minus 1. So you see, it's mostly minus 4, 1. I mean, we can write 1 and 4, right? So 1 and 4 is this is a set of quadratic residues modulo 5, right? So this says whenever we divide any perfect square by the number 5, we can only get 1 or 4 as a remainder. So why is this true? Why can't we get anything? Like, how will we prove there doesn't exist any perfect square which won't give 3 or 2, suppose? Okay, so the proof is not that straightforward. So let's see. First, so claim 1. So let's give this set a name. Let's call this Q5, or QP. Since P is 5 here, we can call it Q5. This is the set of quadratic residues of 5. So let's so observe that if E squared is Okay, I used a, so a squared is congruent to some residue r mod p. Then what can we say about r? So first observe that if what can we say about p minus a, this number p minus a. If we square it and expand it, we get p squared minus 2pa plus a squared. Now the first and the second term are divisible by p, so this is congruent to a square mod p. And we know from our assumption that a square is congruent to r mod p. So therefore p minus a is also congruent to a square congruent to r mod p. So both a and p minus a give the same remainder, right? So now you see out of the numbers p and p minus r, one of them has to be less than p minus 1 by 2, since they both add up to like p. Each of them can't be like each of them have to be strictly less than p by 2. Since p is a prime number, we have assumed, so p by 2 is of course not an integer. We're assuming p is an odd prime number. So assume p is an odd prime. So p by 2 is not inside integers. This implies r plus p minus r is equal to p, right? And r and p minus r are strictly less than p by 2, which implies r and p minus r are less than or equals to p minus 1 by 2. So we have shown r and p minus 1 are less than or equals to p minus 1 by 2. R, not r and p minus 1. I mean r or p minus 1. Okay, so let me make that clear. So r or p minus 1. So both of them are greater than p minus 1 by 2 at the same time. That will make the whole sum greater than p. Right. So we have all the numbers in the set QP, which are made up of R1, R2, R3 up till we don't know how many. So let's say RK. So for all Ri in QP, Ri less than P minus 1 by 2. That's the first result. Next, claim 2. We want to show 1 squared, 2 squared up to P minus 2 squared. These are precisely the quadratic residues of P. I mean, whatever number they give as remainder, those numbers are quadratic residues mod P. So how to show that? Suppose R squared is congruent to S squared mod P. Suppose two perfect squares are congruent to each other modulo P. Okay. Uh, and also assume, and also suppose both R and S are strictly less than P by 2, that's they're less than or equal to P minus 1 by 2. So bringing S on the same side as R, We have r square minus s square is 0. That's r minus s times r plus s is congruent to 0. So we have something that's perfectly divisible by p, right? So since p is a prime number, it can either be contained totally in here or in here. So either the first factor is divisible by p or the second one is divisible by p. Now we have assumed s and r to both be less than p minus 1 by 2. That forces r minus s to also be less than p minus 1 by 2. There's inequality, okay? So that implies p doesn't divide r minus s. Since if this can only happen, or we should write like, yeah, this implies p divides r minus s if and only if r is equal to s. In that case, r minus s would be 0 anyways. So that's one possibility. The second possibility is the second factor. P is contained in the second factor. So what can we say about r plus s? So r is in between 1 and p minus 1 by 2. So and s also has the same thing. This is a comma here in between, not a product. So so if we add the two inequalities, like one is less than, let me do it here. So we have r in between 1 and p minus 1 by 2. Similarly, s is in between 1 and p minus 1 by 2. Add them up. We have r plus s in between 2 and p minus 1. It's basically there will be a plus 1 since this is not exactly, or we don't, like, let us keep it p minus 1 by 2. P minus 1, right, yeah. So r plus 1 is less than p minus 1. Right, so what does this imply again? Like we had assumed p to divide r plus s. We had hoped p to divide r plus s. But as we find p minus 1 is greater than r plus s, so these numbers have to be equal to 0 for p to divide r plus s. This implies r plus s is 0, just like in the first case, uh, which implies r equals to minus s. Right. And our condition, like our initial assumption on r and s, makes it impossible for s to take s or r to take up any negative values, right? It's greater than 1. So this case doesn't yield any solution. So the only possibility we have is if r is equal to s. So therefore r is equal to s. That's the inference. So let's see how to prove claim 2 now from this fact. So we showed that if any perfect square is congruent to any other perfect square modulo p, we have their sum equal. We have their difference equal to 0, or they are themselves equal to each other. So see, they are not only congruent to each other, they are actually equal to each other. Like this would have implied like r is congruent to s mod p, but we are getting more than that. We are getting r and s to be equal. Okay, so that means, so you see, what is the complete residue class modulo p? Like what is the set of all possible remainders when anything is divided by p? It's 1, 2, 3 up to p minus 1, right? And out of them we know that these r and s, or whatever they are congruent to, they are suppose congruent to some a. R square is congruent to A square is congruent to A. So all of them can only be like other perfect squares. So like this set, so they satisfy our first claim, that is each one of them have each one of them are less than or equal to p minus 1 by 2. I mean when divided by mod p. Yeah, so that just infers these numbers are exactly the um, exactly the elements of the quadratic residues of P. Okay, so what does that tell us? It tells us the quadratic residue has a size of exactly equal to P minus 1 by 2, and after some time we will notice that this number is exactly equal to twice of phi of P. This phi function is called Euler's Totient function, which is like returns the number of numbers less than p and relatively prime to p. So when are two primes when are two numbers relatively prime, so two numbers a and b are relatively prime or co-prime when GCD of a and b is equal to 1. That is, they don't share any common factors. So this phi p is actually can be computed easily as p times 1 minus 1 by q1 times 1 minus 1 by q2 times dot dot dot. But this q1, q2, these are all the distinct prime factors of p. Here, of course, p is a prime number itself, so it only has one prime factor, that's the number itself. So we have 1 by 1 minus p, that's p minus 1. So phi of a prime number is equal to p minus 1, right? So that's why I wrote here twice p minus 1. So like the set of numbers which are less than p and relatively prime to p is also called the reduced residue class of p, and it has a size which is called uh, phi p, or the Euler's function of p. There's a lot of jargon here. Basically, if you have a number n, then we have three things. One thing is the set 1, 0, 1, 2, 3 up to n minus 1. That is the set of all residues or set of all remainders of for number n, like all possible remainders, anything else is divided by n. This is called the complete residue class. And then we have a reduced subset of this set, like say suppose 1, 3, 5, 7, something like. You have to fix n for to know what this set is. This is called the reduced residue class. These class, the numbers here here have GCD of 1 with n, right? And then we have the residue class. Sorry, then we have the quadratic residue class. So let's take an example to understand this better. So let's n equals to 13, or p equal to 13, whatever you want to say. So we have three sets. So for 13 we have 0, 1, 2 up to 12 as the remainder set, or the complete residue class. This is the CRC, complete residue class. And the reduced residue class is 0, 1, 2 uh, up till 12. Sorry, not 0. I mean 1, 2, 3 up to the 12. So all these numbers have a GCD of 1 with 13. This 13 is a prime. So this is the residue class, reduced residue class. And then as for the quadratic residue, check what it can be. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So according to our claim 2, from our claim 2, these numbers, these 12 numbers, the square of these 12 numbers can only be our quadratic residues. So take squares and find the remainders to get the quadratic residues, the set of quadratic residues. It's not a class or anything since it's not a group. So it's just a set. So for 1 we have 1, for 2 we have 4, for 3 we have 9, for 4 it's 16, so 3, 5 it's 25 for minus 1, 6 is 36. How much for that? I guess 39 is divided by 13, so minus 3, and it's 49. What's 13 fours are? So 13 times 4 is like 52. That's still quite far away, but minus 3 I suppose. 8 is 64, 65 minus 1. 9 is 81. 13 sevens are 91, unfortunately. 13 sixes are 78, right? So we have plus 3. Then 100, that's 9. And 11 is 121. So basically 11 is minus 2 mod 13. So minus 2 squared is plus 4. So you can back calculate that and take a shortcut. And 12 is similarly minus 1. So minus 1 squared is 1. So basically the set of quadratic residue is 1, 3, 4, 9, minus 1 and minus 3. Pretty large. So there are six numbers in it. Okay, so that was all about quadratic residues and not all about residue classes, since there are other theorems too. So let's solve a problem regarding these quadratic residues. This is the first problem from excursion. It says, look at the sequence 1, 11, 111, 1000 and 111, so on. So let's call Tn as the nth term. So it's 1, 1 up till n many ones. Show that Tn can't be a perfect square. So any idea how to proceed? You see perfect squares. That's what we are talking about for the last 15 minutes or so, I guess. Yeah. So we just have to. So idea is to find some prime number, some suitable prime number, and then like argue why the remainders that these numbers of the form 111 give are not in its quadratic residue class. Sorry, not class, quadratic residue set. That should be enough to say none of them are perfect squares. So let's experiment with some of the first few primes. The first prime that comes in our mind is 3. So what is the residue quadratic residue set of 3? It's 1 and it's 1 and minus 1. I'm joking. It's 0 and 1. Sorry, I forgot to add 0 here. In, in that case, yeah. So quadratic residue have nothing to do with like quadratic residues have nothing to do with reduced residue class, since this is not even a class, right? Yeah. So the quadratic residue set of 3 for 3 is 1 and 0, and for 4 it's, you can check, it's 1 and 0, of course, and then it's, oh yeah, it's just 1 and 0. For 4 it's 1 and 0. For 8 it's 0, 1 and 3. For 5 it's 0, 1 and minus 1. I guess, is that so? Yeah. So do remember along with that for 16. So for 16 it's I guess 0, 1, 0, 1, 3 and 8, I suppose, or not required, right? So these four are enough. Do memorize them. Mostly whenever you need to solve for, or you need to prove something is a perfect square, something is not a perfect square, just divide by these numbers and try to find the remainder, whether or not they lie in these sets, in these quadratic residue sets. If they do, then it becomes a bit difficult to rule out the chance that they can be perfect squares. But if they don't, then simply say they can't be perfect squares. So let's check for 3. So what's 3 divided by 11? So we have 11 congruent to 3 mod, sorry, 2 mod 3. So that's of course not in 3's residue class, right? So 3 can be a candidate for our proof. Let's continue. So 111. So 111 is like 11 times 10 plus 1, and 10 is and 11 is congruent to 2 modulo 3, and 10 is congruent to 1 modulo 3. So that's 3. So that's 0 modulo 3. Alas, 3 divides 111, and you see 0 is in, so 0 is here in the quadratic residue set of 3. So we can't use 3 as our candidate, as our prime candidate for proving that this sequence doesn't have a perfect square. So let's move on to the next prime, 5. So 11 is 1 modulo 5. Again, we are stuck since 1 is in the residue, the quadratic residue class, quadratic residue set of phi. Just a minute. Let's move on to 4. So for 4 we have 11 is -1 mod 4. So it's okay since 4 -1 is not in the quadratic residue. Then 3 ones. First we have 1 congruent to 1 mod 4, which is although inside 4, but we don't need to consider it since okay, let me say it like this. Let me remove 1 from the sequence since it can produce exceptions. So 111 is like 1 times 100 plus 11. 100 is 0 mod 4, so it's 11 mod 4. And 11 is again -1 mod 4. So it still holds. -1 not in residue, quadratic residue for 4. Then 1111, 4 ones is congruent to 11 times 100 plus 11, which is congruent to 11 since this thing is divisible by 4. And 11 is again -1 mod 4. So you see, consistently for 3 consecutive terms of the sequence, we are getting -1 mod 4. So there's an expectation that Tn is congruent to -1 mod 4 for all n in naturals, right? And that would be excellent since that would imply none of them have a perfect square. So let's see why this is true. It's pretty simple. So what do you have? You have n ones. You don't even need to use induction. Just say for n, so Tn is this thing. For n greater than 2 or greater than 3, greater than 3, we have, so take the first n minus 2 ones, multiply it with 100 and add 11. So this is basically what the number Tn is. It's a lot of ones times 100 plus 11. And 4 divides 20 and 20 divides 100, so 4 divides this thing. So this is congruent to 0 plus 11, which is congruent to 11, which is in turn congruent to -1. And -1 is not in the residue class of 4, quadratic residue set. And -1 is not a quadratic. Sorry, someone wrote something in the chat. No, okay. -1 is not a quadratic residue of 4, modulo 4. So Tn can't be perfect square. Right, so another application. Another application is problem number 16 of excursion, exercise 1.1. So prove that so for n greater than 4, 1 factorial plus 2 factorial plus 3 factorial up till n factorial is not a perfect square. So try this problem for a few minutes, then I will discuss solution. So, so for 5 minutes, I'm muting myself. Okay. So could anyone prove this one? Shonok? Hello? Hello, Shonok, can you unmute?
Yes, sir.
Yeah, so could you find any uh, possible candidate or a divisor so that we can check its quadratic residue class? So must have tried for the first few numbers like 3, 4, 5, 6, right? Uh, so the answer would be 10 in this case. So we will check for the quadratic residues of 10. So let's find out what they are. So 10 minus 1 by 2 is, oh yeah, that won't work since 10 is not a prime number. So we have to check for all the numbers. Cool, it's not difficult since dividing by 10 is equivalent to checking the units digit. So take squares. 0 is 0, 1 is 1, 2 is 4, 3 is 9, 4 is 6, 5 is 5, then 6 is 6, 7 is 9, 8, 8 is 4 again, 9 is 1, and that's all. So we have 0, 1, then 0, 1, 4, 9, 6, sorry, 4, 5, 6, and 9. So these are the quadratic residues modulo 10. And let's see what this number, what's the unit digit of this number is, or what is the remainder when 10 divides this number. So 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, 4 factorial is 24, and 5 factorial onwards. We have 0 in the unit digit, right? So 5 factorial is 120, 6 factorial, I guess, is 720, 720, and so on. So how can you guarantee that after the first 4 terms, all of them have a 0 in the unit digit? So that's easy, since after from 5 factorial onwards, from 5 factorial onwards, 2 and 5 both are present in k factorial for all k greater than or equal to 5. Therefore, k factorial is congruent to 0 mod 10. So the remainder is 0 and divided by 10. So the first 4 terms only contribute to the units digit, and that's 1 plus 2 plus 4 plus 6. So that's 33, I guess. The unit digit of 3. So 33 is congruent to 3 mod 10. Therefore, sum over k factorial, k runs from 1 through n, is congruent to 3 mod 10. And observe that 3 is not in here. The quadratic residue set modulo 10. So 3 is not in here, so none of them are perfect squares. And 3 not inside Q10. Hence, sum over k factorial can't be a perfect square for all n greater than 4. So that's that. And next, I'll move on to the next theory. But that's enough examples. So Fermat's theorem. Yeah. So Fermat's theorem says if we have a number a and a prime p, so this over here is co-prime to p, and this is a prime number. Then a power p minus 1 is congruent to 1 mod p. That is, there exists q in n such that a power p minus 1 is congruent, not congruent, is equal to qp plus 1. So a power p minus 1 gives remainder 1. So that's pretty nice to be true, since that says we can always find the power of a if it's, of course, if p doesn't divide a, such that it gives a remainder 1. So these have a name, right? Like if for any number a and if for any divisor n, if a power x is congruent to 1 mod n and a power x, and a power y, or let me write it on the side, a power y is not congruent to 1 mod n for all y less than x, then we say x is a root of the equation a power x congruent 1 mod n. Right, these are called primitive roots. So primitive root modulo n. So here p minus 1 is not necessarily a primitive root of a, since there can be others less than p minus 1 which give 1. But this is at least a multiple of that, right? So primitive root of a divides p minus 1 if p is a prime and doesn't divide a. So proof. So how do we prove this? So we look at this set 1, 2, 3 up to p minus 1 or n minus 1 in this case. Oh, sorry, it's p only. I used n for that example. So P is this prime, and we want to show a power P minus 1 is congruent to 1 mod P. So we look at this set. This, if you can identify, is the reduced residue class mod P. So it's the set of all remainders except 0, since P, anything that P divides, it can only be congruent to 0 mod P. So we don't want to include those things which have a common factor with P. Now let's say you multiply A with each of them. So you get the new set A, 2A, 3A up till P minus 1A. So my claim is this is that same set RRC when divided by under modulo P, or when each one of them is divided by P and exchanged with the remainder. So why is it true? So say suppose any one of them, suppose Ka. So Ka gives some remainder Rk mod P. What's the uh, what's the inequality for Rk? Rk can be at least 0, and it can be at most P minus 1, like any remainders of P. Okay, now let's so we have P and A GCD to be 1, since we have assumed A and P to be relatively prime. So that implies P doesn't divide A. So that implies if Rk is equal to 1, so sorry, not R1, 0. So if Rk is equals to 0 mod P, that implies K is divisible by P. And that would force K to be divisible by P, since A is not divisible by P, right? And that can't happen, since you see we have taken the set A, 2A, 3A up till P minus 1A, and none of them have, like, we haven't taken 0A. We had excluded 0 from our set way before, when we took our reduced residue class of P as our starting set. So this can't happen. So we can modify the inequality of Rk to be something like this. So we have ruled out the case where Rk can be 0. Now let's suppose Ri equals to Rj. Not equal, I mean Ri congruent to Rj mod P. This is also congruent. Can we say now? So the corresponding Ia is equal to Ja mod P. And similarly, if we take them on one side, I minus J 0 mod P, and P doesn't divide A, which implies I minus J is divisible by P for this to hold true. And that implies I equals to, I and J are congruent mod P. Now observe that both I and G are basically in the set 1 up to P minus 1. So if they are congruent, that would mean they are equal, since numbers which are less than P are not changed by congruence. Like, they are the remainders, right? P can't divide them further. So this implies I is equal to J. So that shows if like any Rk, all the Rk's are different and none of them are equal to 0. And we know and how many RKs are there? There are as many RKs as there were Ks in the set, the reduced residue class of P modulo P, right? So let me write them down. So all the RKs are distinct and none of them are 0. And all of them are in between 1 and P minus 1. So the only possibility is is this set 1, 2, 3 up till P minus 1. See, there are just exactly P minus 1 numbers and all of them are distinct and none of them are 0. And we know what that set is. That set is the reduced residue class of P, the one that we just started with. So this set and this set, they are equal. Proved. Okay, so how will this help us? So we proved that if we multiply a co-prime number with with P's reduced residue class, or this set 1, 2, 3, 4 up to P minus 1, we get the set again, the same set again. So we can multiply the elements of P on both sides, elements of the set on both sides, right? So on the left hand side we get a power P minus 1 times product of I runs from 1 through P minus 1 I equals to, yeah, of course these sets are not equal, they are equal, they're congruent under mod P. So this product is basically P minus 1 factorial. So P minus 1 factorial times a power P minus 1 is congruent to P minus 1 factorial mod P. Now if you remember the division rule, we can divide P minus 1 factorial on both sides. This is a condition that you have to ensure that the divisor P here doesn't divide the thing that we're dividing on both sides, that is P minus 1 factorial, which is true since as P doesn't divide P minus 1 factorial. Why is that true? Since this has only the factors which are less than or equal to P minus 1. And all of them can't, like, none of them can divide P since P is a prime number. Right. So they don't divide P. So this shows a power P minus 1 is congruent to 1 mod P. That ends the proof. Right, so yeah, this proof was a bit tricky since you have to start off with this reduced residue class and think of multiplying it with that number A. But one motivation was there, since we had to find P minus 1 factors of A from somewhere. And we know from experience, or as we just saw earlier, that the reduced residue class has exactly P minus 1 many numbers. So where did I write that down? Yeah. So there are p minus 1 numbers in the reduced residue class if p is a prime number. So that p minus 1 and this p minus 1 made us wonder why can't we just multiply them and try to find something interesting relation. Okay, so the next theorem we have is Euler's theorem. Then we'll move on to problem solving. So this is also pretty similar to the last theorem. It says a power 5p is congruent to 1 mod p. So here p may or may not be a prime. And the condition that a and p are co-prime, that I guess that doesn't hold. Let me check just once. Oh yeah, that condition still holds. So GCD of a and p is still 1. So this only holds if a and p are co-prime. Right, so proof is exactly similar to the previous one. We take the reduced residue class of p in this case, but now we are not sure whether it contains exactly p minus 1 things or less than that. So for that I'm just writing it as R1, R2, R3 up till R5p. So one thing we're sure about it, that it has exactly 5p many elements. What is 5p? 5p is exactly that, the set of elements in the reduced residue class of p. Now moments before I said 5p is equal to p times 1 minus 1 by q1 times 1 minus 1 by q2 dot 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 till 1 minus 1 by say suppose anything r. So if p has r prime factors, then these are the r prime factors q1, q2, q3 up to qr. Then this formula gives the value of Euler's Totient function of p. So where does this formula originate from? Well, it comes from the principle of inclusion exclusion. So side 2, we have a side 2. Let's see what principle of inclusion exclusion is. So it's an idea of combinatorics. The idea is there are certain things. Combinatorics is the subject, is a branch of mathematics that deals with counting problems, like how many ways can people be arranged in a team, how many ways can you put boxes or birds in boxes, and so on. So in many a times we find it difficult to count certain things, since the constraints or conditions imposed on it are pretty difficult to like enumerate. So then we just simplify those constraints and then again subtract the ones that like get a larger number of cases and then subtract those cases which we don't want. So that's the principle of inclusion and exclusion. Here as an example, we have to find the number of numbers which are less than p and relatively prime to p. So this is the combinatorial problem. We are solving it with principle of inclusion exclusion, also sometimes called sieve. Okay, so sieve. So how many factors of p are there, uh, or like how many numbers are there less than p? So there are exactly p many numbers which are less than p, namely 1, 2, 3, 4. Well, let me include 0 also, up to p minus 1. So this can be the maximum possible set of reduced residue class. Like we have to eliminate a few numbers from this which have GCD of greater than 1 with p. So let me write minus. Next, how many numbers are there uh, which share a factor of 2 with p? So there are p. So p. Remember, p is not a prime number here. So if for a number to share a a factor of p with p, uh, p has to be divisible by 2 first. So if p is divisible by 2, we have p by floor of p by 2 many numbers which share a factor of 2. So what is floor of p by 2? So floor is the least integer, sorry, or greatest integer function, or floor FLOOR, or box function, sometimes also called Dirichlet's function. So basically, if you have a number on the real line and these are the integers, so it's 0, minus 1, minus 2, 1, 2, 3, 4, 5. Suppose you have some number here in between 2 and 3, then floor of that number is exactly the integer on the left. So suppose the number was 2.14, so floor of 2.14 is 2. Similarly, the floor of any integer is the integer itself, and the floor of a negative number is the number onto its left. So the floor of minus 0.67 is minus 1, not 0. Okay. Yeah, so let me continue. So this is the number of numbers less than p, and p and that number, let me call that n, have a GCD of uh, exactly 2. Not exactly 2, but at least 2. Yeah, at least 2. Then similarly, we have numbers p by 3, floor of p by 3. These are the numbers which have a common factor of 3 with p. And now we have overcounted a few numbers, like those numbers which had a common factor of 6 with p are counted both in here and in here. Right, since they share a common factor of 2 and 3 both. So I've subtracted it twice from p, so we have to add that back. So adding that back, we get this. And then we have to continue like this, like then we have to divide by p, then we have to add p by 15 and p by 10. And since we have, while doing this, we had again triple counted or triple discounted Like, sorry, what am I saying? Actually, we have just discounted py like 2 into 5 into 3. That's 30, right? Yeah. So we have to add that. Sorry, not add, subtract that again. So that just goes on. So compactly we can write it as p equal, not p, phi p is equal to p minus sum over qi such that qi divides p and qi prime box of p by qi. So this is basically phi p. So let's try out for the number 10. So the residue class, or the complete residue class of 10 is 0, 1, 2 up to 9. So what is the reduced residue class? Let's try to do it manually first. So 1 and 10 have a GCD of 1, but not 2 and 10. 2 and 10 GCD of 2, so we can't take 2, we can take 3. We can't take 5, we can't take 6, we can take 7, we can take 9, and that's all. So this is reduced residue class of 10. So it has a size of 4. So let's see. So phi 10 has to be 4, right, from definition. So let's see if this formula on the left gives us that. So this is 10 minus sum over floor of 10 by qi. Qi divides 10. So how many prime factors of 10 are there? So we know 10 equals to 2 times 5. So there are just 2 prime factors. So this is just 10 by 2, 10 by 5. This is a 5, and plus 10 by 10. So that's 10 minus 5 minus 2 plus 1. So that's 10 minus 6, 4. So you get 4 right. Now in the intermediate step, if you want to simplify it further, we have 10 minus 10 by 2 minus 10 by 5 plus 1. And that's 10 times 1 minus 1 by 2 minus 1 by 5 plus 1. Take common half minus 1, and yeah, again take common half, take common minus half, or I guess, yeah, you can basically just check if 10 times 1 minus half times 1 minus 1 by 5 is what? So it's 10 times, oh yeah, that's why it wasn't matching, it was 1 by 10. Okay, so it's 10 times, taking common half, or sorry, not half, 1, we have 1 minus half, then minus 1 by 5, 1 plus, no, sorry, 1 minus half again, so it's 1 minus half times 1 minus 1 by 5, and that's the usual form of the formula we are used to using. Oh, sorry, we were trying to prove Euler's theorem, not a Totient function. So that ends our sidetrack. Let's return back to Euler's theorem. So now for Euler's theorem, we know this set R1, R2 up till R5 P is the reduced residue class of P. And now, as in the previous problem, we multiply this with A. We get AR1, AR2, AR5 P, and then argue similarly that so how do we argue? We say if any two of them are equal, so if R1 AR1 is equal to ARI is equal to ARJ, that means ARI minus RJ. I mean, if they are congruent mod P, right? So here again, since P and A are co-prime, so P doesn't divide. So since P doesn't divide A, this implies Ri minus Rj has to be 0 if their product is 0, and that implies Ri is equal to Ri is congruent to Rj, and since both of them are less than P, so that implies Ri is equal to Rj in turn, and which shows so Ri's are all distinct as before, and it's also obvious that Ri is greater than 0, since any of them being equal to 0 will mean either A was divisible by 0, or if Ri's are divisible by 0, that's not possible, since by definition Ri is relatively co-prime to P. So we are again left with the only possibility of Ri being the set R1, R2 up till R5P. So that is the set AR1 up till AR2 up till AR5P. Now, whenever I am saying that these two sets are equal, that doesn't mean R1 is equal to AR1 and R2 is equal to AR2. Like, they can be permuted in any order. For example, like R1 can be equal to AR5, while R5 can be equal to AR6. Obviously, R5 is R5 can also be equal to AR1, but yeah, anything can happen. So let's take an example. So we had computed the reduced residue class of 10 before. So it's here, it's 1379. So 1379. So this is the RRC of 10. Now let's find some suitable A, which is co-prime with 10. And let's make it, let's have it larger than 10. And let's not take it, let's not take a prime number, since that won't be interesting. So co-prime larger than 10 and relatively prime to 10. So it can have factors of 3 and 7. So let's take 21 instead. So what is A times that set? So 21 times that set is 21. and so there's mod p, of course, lingering in the back. So twice. So mod 10. Mod 10 is just same as taking the remainders. So it's 1379 again. So here, so here you see we have a 1-1 mapping, R1 here was 1 and A times R1. So 1 times 21 was 21, which again gave remainder of 1. So gave 3 times 21 a remainder of 3 and 4 times 21 remainder, 7 times 21 remainder of 7. But they can permute, they mostly permute. Sometimes they have inverses. We will talk about inverses later in some other day. Okay, so that was all about Euler theorem. Let's solve some exercises. So the first easy problem is if n is a natural number, yeah, of course, and the GCD of n and 35 is 1, then show that n power 12 is congruent to 1 mod 35. This is the very first problem. I will solve it for you. So observe that 35 is 5 times 7. So it's a composite number composed of 5 and 7. And since n and 35 has a GCD of 1, it implies n and 7 and n and 5 also have a GCD of 1. So now we can utilize Fermat's theorem since we have got two numbers which are relatively co-prime, and cherry on the top we have prime numbers also. So we can basically use Fermat's theorem also if we want. So from Fermat's theorem, n power 5 minus 1 is congruent to 1 mod 5, and so is n power 7 minus 1. Now that means n power 4 and n power 4 is 1 mod 5, and here we have 12, so whole power 3, so 1 mod 5. Similarly, n power 6 is 1 mod 7. So taking squared, we have n power 12, n power 6 squared, 1 squared, 1 mod 7. So this and this both imply n power 12 is congruent to 1 mod 5 into 7. That's 35. why is it true? Like, I forgot to tell you this. Like, if A is congruent to R1 mod N1 and A is congruent to R2 mod N2, then both of them imply A is congruent to not R2, R1. Both of them are, why am I writing 1? Like if A is congruent to R both modulo N1 and N2, then A is congruent to R mod N1 times N2. Proof is pretty simple. Just write A as Q1 N1 plus R, and also A is equal to Q2 N2 plus R from the definition of congruence. And now just what can you do? Multiply each one or substitute. Okay, let me multiply. So multiplying it by N2. Here we have an additional thing, that is GCD of N1 and N2 is 1. That's important. So we need to write A equals to Q3 times N1 N2 plus R. And to show that, okay, just equate both of them. So we get Q1 N1 plus R equals to Q2 N2 plus R. R gets cancelled out. We have Q1 N1 is Q2 N2. Right, and now observe, if N1 and N2 have a GCD of 1, that implies N1 divides LHS, which implies N1 divides RHS, which implies N1 divides Q2 times N2, and N1 and N2 GCD of 1, so N1 can't divide N2. And since N1 doesn't divide N2, so N1 divides Q2. Similarly, since it's symmetric, N2 divides Q1. So basically, let Q1 equals to Q3 N2. That implies A equal to Q1 N1 plus R equals to Q3 N2 N1 plus R, substituting the value of Q1 from here. And that's why N1 N2 divides A minus R, or A is congruent to R mod N1 N2. Okay, so and what would have happened if also look at this equation. Also, if not A, N1 N2 had a GCD of say G, then we have to first divide the GCD on both sides. So then we have Q1 by N1 dash, Q2 by N2 dash, where N1 dash or Ni dash is Ni by G. And then now we would add, since g is gone, we have n1 dash and n2 dash is equal to 1. From the fact that if a and b have GCD of m, that implies a by m and b by m have GCD of 1. Pretty straightforward. You can just argue with factors of m and right. And then the steps follow as in here. So that justifies why we can multiply these two equations and the divisor of the modular, since they are co-prime themselves. And it also proves our claim. Okay, so it's already about to be too late. So before that, let me post some homework and call it a day. So first question is, find the last two digits of 7 power 100 minus 3 power 100. So mind you, last two digits, not just one. Next is, show that sum over phi d, uh, where d divides n, is equal to n. Obviously, d can only be less than or equal to n. The last one is, okay, try proving this one. Show that sum over r runs from 1 through n minus 3. R times r factorial is divisible by n if and only if n is prime. So try out these three problems and we will meet next week. Good night.